Okay, welcome everyone to this continuation of quantum topology. Quantum topology, and today I would like to tell you a little bit about why it's actually called quantum topology. It's a bit mysterious. There has been no quantum, no, not really any topology at this point, right? So neither quantum nor topology. So quantum topology is neither quantum nor topology. I actually don't know who came up with the name itself. I don't know. If you do, let me know. I would be very interested to know that. But essentially, it's a mixture between something that comes up in topology, which is a Reidemeister 3 move. We'll see that today. And something that comes up in quantum theory, if you want, quantum wave here, namely the Young-Baxter equation. And turns out they're the same. And the realization that they're the same essentially burst this field of quantum topology. And we'll start by exploring that by looking a little bit on three-dimensional things. So that's where low-dimensional topology starts. So what I'm looking at is the braiding. So I will add another categorical operation to, well, our monoidal category setup. And I will call that thing a braiding. And the braiding really comes from braids. So like hair braids or mask braids. So what we want to do is we want to get invariants of knots. And braiding is really the categorical avatar of crossing of strands. Essentially, there's a swap, which I come back to in a second, and we kind of make this a little bit nicer and distinguish between whether we swap over or we swap under. And the swap itself, kind of another interesting fact here, everything is based on linear algebra, is literally just a permutation matrix operation on a vector space. That's it. It's just really just permuting things. You just swap them over. Now you have AB and you swap them to BA. That's literally it. And kind of the magic observation, which is roughly 30 years old by now, maybe that's a better way of saying it, which came up in the 1980s, is that this swap map can actually be used to generate invariants of knots. So it can be used in low-dimensional topology to say something about knots. And this is where this word, topology comes from. And the quantum comes from the fact that the way, it's not quite the swap itself, the vector space swap. That one is a bit boring as a map. You don't get really great knot invariants. You don't get much information about your knots. But there's rather a quantization of that thing, which people usually draw as a crossing. And that's where the quantum comes from. So topology is really more low-dimensional topology. And quantum is meant in the sense of, well, instead of kind of a planar crossing where you can't see anything because you just swap factors, you can now distinguish between over and under. Yeah? And that's literally where all of this comes from. And then we just piece things together, right? Pivotal or duality, what we had, like cups and caps, they come from vector space duality. And both of these structures together are somehow enough to generate enough in quotation marks to generate plenty of examples of applications in low-dimensional topology. It's kind of an interesting part of the story. But for today, the only thing you really need to know is that braiding is kind of a categorical avatar of crossing of strands. But what I mean by that is usually you have a knot, which is a three-dimensional object, right? You can build it out of rope or something, but you usually only study it in a projection, which is a two-dimensional object, and then strands cross over and under. You literally just project it down and remember which one came first in your little projection down to. So like here, if you project from here and then you hit this strand first, so this one comes over and this one goes under. Something like that. And turns out that you can make it a bit easier. Kind of the basic building blocks are actually braids. So braids is kind of a fun topic. Here's a braid. I kind of dislike a little bit the Wikipedia page on braids because they give this really nice picture of what a braid is. Yeah, a braid is literally just you have a certain number of strands and you're allowed to cross them over and under, but you're somehow not allowed to in the end. Then they have to go from certain points to certain points. It's a bit more rigid than a knot itself. And then the Wikipedia page decides to have this beautiful picture, and then Well, braid group, let's see. Then they do this, braid group, braid group on Wikipedia. So you have this beautiful picture, and then they decided to draw them sideways. I don't know why. Anyway, I will draw them in this direction. I mean, that's just, of course, just a matter of taste, but I kind of feel a little bit, if I have one picture going in one direction, I somehow shouldn't have another picture going in the other direction. But anyway, Wikipedia is otherwise pretty great, but this was a bit annoying. Anyway, I will draw the braids like this, and braids is really just, you have those braiding, kind of a knot in a rectangle, if you want. You push a knot into a rectangle, and that's a braid. And if you can imagine that you close this thing off, then you get a knot. So kind of the idea is that braids generate knots in a sense, but are much easier. You put them in a rectangle, in a little box. And in category theory, we like boxes a lot. Or string diagrams sit in boxes as well. So great. So maybe we can just mimic braids. That's literally what it is. And usually braids are generated by crossings. Let's say call them sigma. Like that goes under, this goes over, this goes under. This would be a bunch of crossings that you can do. Here's another one. And you just stack them together, right? You just cross various strands. And now I pull up my Wikipedia strand again. So here, sideways, as I said. But essentially, the braid group is generated by these little just swaps. And then you can just generate more complicated pictures by composing them. Kind of tricky here is this is not a braid. So you don't have any turnbacks. It's literally just the only things that you can stack together from crossings. Okay, so that's a braid group. It's much easier. You just have crossings and you generate the braid group. And that's what a braiding mimics. It's essentially a category with an action of the braid group. So you have something that kind of in your category behaves like a crossing of the braid group. That's literally what it is. And if you wanted to have the definition in one line, and we do go into more details later, the definition in one line is the braiding is natural isomorphism from two objects, x and y. No, here we have here we have x and whatever it is, x and y and a, I guess. Y and a to a and y, right? X and y to y and x and y to y and x. Oh, very complicated. You should just use a and b, I guess. Anyway, it's literally the swap map, right? And you take a factor x, you take a factor y, and you get a factor y, and you get a factor x. It's literally the swap. But you are allowed to not just swap. It could be any map that satisfies a certain number of axioms, and that's why people think of it as a crossing, because usually it's not self-inverse. So you can't undo it. If you just swap AB, BA, then it goes back. But here, it could be AB, BA with some little twist. So like here, if you do it twice, it's somewhat twisted over. Something similar, you allow something similar here. And then you have the usual condition that you would add, because it's category theory. Naturality, swapping factors behave nicely with F and G. In pictures, here's F, here's G. The crossing is natural. For me, this just means I can take this little box F and just scroll it, just move it over because it goes over the understring. And I can take this little box G and move it under because the string goes under, and I get that picture here. Yeah. So just swap them over. That's just. But that's literally what naturality will mean. And coherence is a similar picture that we will see. That's literally a braiding, a choice of an image of the braid group, essentially. You need to have the one equation, which is the underlying equation that determines everything in quantum topology, if you want. And it goes under various names, so the Reidemeister 3 move or the Young-Baxter equation. And interestingly, so this is a knot theory version, and this is like the physics version, if you want. And they're the same, essentially, up to some minor details. And people realized that in the 80s, as I said, essentially, and then came up with, well, not invariants, from physics, essentially. No? So that's what quantum topology actually is. And it's a very nice, easy equation. So literally, you can just stare at it, and it's true, right? So you have this crossing here, which is in front. This strand is like in the middle, and you just pull it over. That's like the Reidemeister 3 move. or the whatever you want, sliding one crossing past another, or the Young-Baxter equation, whatever you want to call it, right? So x goes all the way over to here, and here x still goes all the way over, z goes all the way under, z goes all the way under, and y is somewhat in between, so you can just arrange y to different sides. In the braid relation, this is a famous Reidemeister relation, or sometimes people even call it the braid relation, because it's a defining relation, essentially, of the braid group. And categorical, we will encode this in a funny identity, which we call the hexagon identities, which I'm not going to pull up here. And this C should be a beta, because it was a braiding and not a C. Okay, so that's what we're going to do. So braiding, a braided category will just be a category with a braid group action. That's literally what it is. A braiding gives a braid group action on 10 to the powers. Huh? A category with a braid group action. And otherwise you would have like what people call a colored braid group action. Don't worry about that too much. Essentially there's a braid group action in your category now. And then you would expect braid groups, that's something three-dimensional. Maybe you can use that to cook up three-dimensional information. And yes, you can, but you need a little bit more. You need the dualities. In the definition of a braiding, so cups and caps, right? You need turnbacks. Let me pull up the Wikipedia page again. So this is not a braid because you have cups and caps. Braids are not allowed in cups and caps. Braids are more like that. Yeah. Do I get a nice image of braids? Braids are more like that. Yeah. Or both. Well, let's stay here. Braids are more like this. Yeah. So literally, no cups and caps allowed. But you want to both for real topology, right? You want to do the zigzag relation. You want to shift things around. So we need to add them, and then we have the theory of braided plus pivotal, which people usually call like a ribbon or something, right? So there's already then topology, and that's what we already need to invariance from categorical data, which is the whole point what quantum topology promised to deliver, and it does deliver, which is kind of very nice. So you can use category theory, essentially a very rigid type, a very discrete, rigid type of story, if you want. Build it on vector spaces, and then you can produce invariants of knots, which is kind of a very, even more general, of low-dimensional manifolds. Also, I'm not going to do that. So knots and low-dimensional manifolds, which is quite impressive, right? From a rigid data, from a very, very discrete kind of approach using categories, you get invariants of links and other low-dimensional topology objects. Anyway, I hope you enjoyed this video, and I also hope to see you next time.